Hello, and welcome to the Science on 7th live stream, a virtual space where we talk about issues related to air quality and health. I'm your host, Pallavi Pant. And if you've been following this live stream for a while, you will have noticed that we talk a lot about the problem that is air pollution. We think about solutions to fix it and hear from people who are trying to understand the linkages between air pollution and health. And one of the topics that we've covered in previous live streams is how we monitor air quality and the ways in which we are trying to learn more and more about the status of air quality in different places. One of the ways in which we've been monitoring air quality in different regions around the world is through satellites. And this has become really important, especially in places where we don't have ground monitoring. So we don't know what's happening on the ground, but we can still capture information through satellites and try to piece together what the exposures to air pollution might look like for a particular community, use that data to look at health effects, to look at whether changes are occurring over time or not. And today, I'm really excited to be welcoming a very special guest to talk all about satellites and how we can use them, how we have been using them for air quality and health applications. I'm very pleased to welcome Dr. Tracey Holloway, who's a Jeff Rudd and Jean Bissell Professor of Energy Analysis at the University of Wisconsin-Madison. And she's been using satellite data and computer models to advance our understanding on air quality, to inform policy action. She's a member of the National Academy of Medicine and very recently was announced as a 2025 AGU Fellow. So, congratulations, Tracey, on that. And an important one for me is that she's also a founding member of Science Moms, among her many other accomplishments. Tracey, it's really nice to have you here. Welcome.
Thank you so much, Pallavi. It's really a pleasure to be here this morning.
Wonderful. So I'm going to start with, a basic question. When people try to describe satellite data, we often hear about the phrase eyes in the sky. Can you walk us through what we mean by that? And, what is it that we are referring to? We also have some images that we can pull up to reference what this eye in the sky really tells us. But yeah, please tell us more about it.
Sure. Well, I think a good place to start is that when we want to know what is in the air that we're breathing, the traditional approach has been to have an instrument located at the ground level. And that really remains the gold standard because we're all living near the surface of the earth, and these instruments can tell us the chemicals that are right in the air where we're breathing them. The problem is these instruments are quite expensive and they need power supply, they need to be in a safe environment. And so they're very limited around the world. We have none over the oceans, and 70% of the earth is covered with ocean. We also don't have these instruments. Many countries have no instrument at all called an air quality monitor. And even countries with a lot of monitors, still neighborhoods within a city may not be covered, rural areas may not be covered. In the United States, about 80% of counties don't have a single monitor. So this is the starting point, the gold standard. And but satellites are up in space looking down. And because they can see the whole Earth, they really can provide coverage over most areas. That is something that no monitoring system could ever do. So it's not one or the other, but it's how can they work together. And the way that these eyes in the sky can see the chemicals has to do with what wavelengths of radiation different gases absorb, and also for particles, how they scatter the sunlight. So it all has to do with some of those characteristics of gases that people may have learned in physics class back in high school. And there's some gases that are better for the satellites to see, and other gases that the satellites cannot see.
Amazing. So clearly, there's a number of ways in which we could be monitoring this data. But I'm wondering if we go back in time, when did we first realize that satellites could be useful for air quality applications? And from that moment in time, what has been the trajectory and the development of use of satellite data for air quality work?
Well, it was really in the 1960s that actually it was right here at the University of Wisconsin-Madison, where I work, that a professor named Werner Suomi had this idea that we could build an instrument and use it to monitor clouds, weather patterns, other things in the atmosphere. Um, the first atmospheric satellites were launched in the early 1960s. And actually, one of the very first things that they were able to measure is aerosols, particles in the air, a dust storm, wildfire smoke. These are things that just imagine a camera up in space looking down can detect. But over time, the instrumentation on these space satellites has gotten more and more advanced. And so, really, in the early 1990s, there were some instruments that could see gases for the first time. And once we learned that we could see the gases and particles, then there was the question of, can we make these useful to the public health community, to the air quality community? And I think one way to sort of think about this from a science perspective is that, NASA is really focused on sending stuff into space that can do cool things like observe planets or measure galaxies. And there was sort of this question: can we see these gases in the air on Earth? So it was never this idea of, let's supplement the ground-based air quality monitoring network. It was more of a, gee whiz, is this even possible? Um, and because NASA is focused on the science, for a long time, they have funded scientists around what they call science teams. So they would send an instrument up in space, and then they would make sure that there were researchers on the ground who could turn that data into something valuable. But in 2011, they funded the very first, what they called an applied science team. And this was around the theme of air quality. So it was called the Air Quality Applied Sciences Team. And this was saying, we're not going to focus on one instrument, but we'd like the scientists to use all available instruments, models, data platforms, and to try to support air quality management in the United States at that point. And really, over this 5-year science effort, the idea of using satellite data for air quality went from being kind of a niche idea or something a couple people did to suddenly the conversation changed. And it really was, there was a lot more curiosity and a lot more enthusiasm. And so in 2016, NASA renewed that team, but now with a bit wider focus, not just air quality, but health and air quality, and not just the United States, but the US and global applications. And that team has been the Health and Air Quality Applied Sciences team. It's a funny acronym, and we call it HACAST. And I've been leading that team for NASA since 2016, where it first ran from 2016 to 2020, then 2020 to 2025. And we were very happy that it was renewed this year, and it's going to be running through 2029. And the work coming out of that team has really made a big impact on building bridges between organizations like the Health Effects Institute and this billions of dollars worth of data that are all available for free through well-managed data distribution platforms. So it's really just the question: the data are there, the needs are there, how can we connect them?
Fascinating. So to, go from can we do this to now so many applications around the world. I actually want to bring up that image we showed earlier, just to, take a minute to highlight how incredibly powerful some of this data can be. And Tracey, do you want to walk us through, like, typically when we're thinking about, you mentioned sand and dust storms, you mentioned wildfires, and specific sources. When we're looking at images like these, how do we go from what we're seeing on the screen right now? So I can tell, like, the dust is moving, especially in the middle image, but how do we go from this to, here's what the air quality levels might look like, or here's what the air pollution levels might be in a particular location, and what the steps involved in that process might be?
Sure. So first, for viewers who are looking at this image, I think there's 3 images here. They all show a little bit different things, but one thing they all have is sort of patches of white. And in some of the images, the white is snow cover, but I think in other images, it's cloud cover. And something important to know is that satellites cannot see through clouds. And snow makes it difficult for the satellites to see as well. So these instruments up in space are not perfect. They have limitations. And one of the big limitations is that they're looking down. So in the middle image that you have here, we can see a dust storm. We know it's a dust storm because we see a desert and then we see a lot of kind of tan particles blowing in the wind off the shore. But we don't know if that dust is at the surface where people are breathing it or way up high above their heads where maybe they can see it in the sky, but it's not affecting their health. So one of the big questions when it comes to using satellite data is how much of what we see from space is affecting people at the surface where we're breathing. And over the years, there have been a lot of different strategies that have been used to try to connect the view from space with the reality on the ground. And one approach has been some statistical approaches. If you have a monitor on the ground, you can say, is it seeing a high dust event at the same time that the satellite is? But more sophisticated methods have been using computer models because computer models can represent kind of a three-dimensional virtual reality of the atmosphere. And they can estimate if a wind blows, for example, dust off of a desert, how much of that is near the surface and how much of it is in the column. So these computer models are proving to be a powerful way to translate the satellite data into surface concentrations. And taking it a step further, the best available data products to support near surface particulate matter, for example, use information from multiple satellites, from computer models, from ground-based observations, and pull them all together in what is sometimes called data fusion. And this data fusion process can also benefit from artificial intelligence and machine learning. So sometimes the metaphor is made that we're kind of like we're cooking up a recipe where you have different ingredients, and the better the model, the better the satellites, the more comprehensive the coverage of the monitors. Those are the ingredients that are going into this estimate. But there are a lot of different algorithms, including those that benefit from machine learning, that can combine these ingredients to create the best available estimate of surface PM 2.5. And I think that really these data fusion products have played an enormous role in understanding the health effects of air pollution around the world, because it's the first time we have information what people are breathing, even away from monitors, even in countries that have no monitors. And it's been a big part of the work of the Health Effects Institute and your State of the Global Air Report. It has been part of the Lancet Countdown. It's been part of the Global Burden of Disease reports. There have been a lot of global health analyses and rankings that have really benefited from these data fusion products where satellite data is a big ingredient.
Yeah, I mean, that in fact is one of the things that I've truly appreciated about satellite data, that it's an equalizer. We know there's places around the world where we don't have ground monitoring information, but at least with the help of this data and other information, we're able to see what the average levels might look like, how they might vary over time and space. And I will admit that, the estimates are perhaps not perfect everywhere, but they're enabling really good science. In fact, we were recently looking at evidence in Eastern Africa around air pollution and health. And what we found is that over 70% of the publications in the last few years utilized satellite-derived air quality estimates because ground monitoring data isn't available at the scale that they wanted to. So clearly, we can use these data in many different ways. And I think one question that people do ask is, well, if you don't have any ground monitors, how do you validate what your estimates are? Or how do you know that these numbers are real? Can I trust them? This is a question that policymakers sometimes would ask, or even scientists would ask. And can you tell us your perspective on this? And what are the things we should be careful about when using satellite-derived estimates? And then what are the things that we can be really comfortable with using them for?
Well, I think one thing to keep in mind is that different satellite data products have different levels of uncertainty and different kind of rules of engagement. When we're thinking about satellite products, I would say the two kind of superstars are the gas detection of nitrogen dioxide, NO2, and the ability to calculate particulate matter in these kind of data fusion approaches that I've just talked about. So maybe I'll first talk about the data fusion, just to continue what we talked about. Um, though the most of the data fusion efforts that are looking at PM 2.5 are producing monthly average concentrations or annual average concentrations. To my knowledge, there is no daily PM 2.5 from a data fusion product over the United States or around the world. And there may be some over specific areas of the country that have been developed by researchers. So a lot of people want to say, can you just tell me the daily or the hourly PM 2.5 from satellite data? And the answer is no, we cannot. Because many satellites only pass over once a day. As I mentioned, they don't see when we have clouds. And the process of doing this data fusion requires enough data to make it a robust estimate. And I think it is, there's been a lot of evaluation of these data products, and including my group is working with the team out of Washington University in St. Louis to do a lot of evaluation for the United States. Their team has a whole network called the Spartan Network that measures ground-based PM 2.5 around the world. So there's, the evaluation and improvement of these data products is a huge area of research. But so that's, I'd say, PM 2.5 from these data fusion products is the best available at, the monthly or the annual basis. I think if we kind of pivot to satellite NO2, it's quite a different story. One reason it's different is because we don't need to do quite as much processing of the data. We can get an image from the satellite, and it may show cities popping out or a plume from a power plant popping out just from the satellite data alone. Now, that still isn't what people are breathing at the surface, but it can often be used to understand which areas have higher pollution than others, which days have higher pollution than others, and what are some of the major sources of pollution. So I think, when people ask, like, how good is the data product? I would say, how good is it for what? If you're really wondering, like, does it equal what's on the ground? No. But can it be used to trace sources, to understand disparities, to trace transport from one place to another? I think for all of those things, to evaluate computer models, that it really can be used almost off the shelf.
Yeah, that's really good to know. Also, because in the last few years, the one example where I've seen a lot of use of satellite data really is in South Asia, especially in India, with agricultural stubble burning that tends to happen over a period of a few weeks, leads to a lot of air pollution. It's really visible. The fires are visible, and you can track them using satellite data. You can also see how the plumes are moving across time and space. And even on news channels now, we see those maps with the red dots of where the fires are, what's changing on a daily basis. So there's clearly been a lot more uptake of this type of information already. And what's also been interesting is the fact that in addition to NASA investing in this work, we've seen the European Space Agency, South Korea, and others starting to also launch big programs. I think we have an image, if we can pull it up, showing us the constellation of some of the air quality instrumentation that is now starting to be, starting to give us very specific, very detailed data almost throughout the globe. So I'm wondering, as these new data sets and new products become available, are there examples that you can help us walk through where satellite data has been useful either to track changes in air quality, maybe short term or long term, or has motivated someone to take policy action or enabled some kind of policy action? Because that's really what we would like to get to.
Right. That's a great question. So, what you're seeing here is an image from the new GEMS satellite, or not quite so new anymore, but over Asia. There is already an analogous instrument over North America and one coming over Europe. And this is the first time we have hourly data on gas phase pollutants. But we have quite a few other instruments that are already up in space that can provide daily data on gas phase pollutants and hourly data on particles. So, we have this like a toolbox that's constantly growing, and each tool in the toolbox can solve slightly different or better problems. But in the same way, if we have a daily instrument that covers the whole globe, that's fantastic as an equalizer, like you're mentioning. On the other hand, these hourly data sets can provide more time coverage, but only over a certain area, like in the photo or the image where it's really focused on East Asia. You had asked about some examples of the data in action. I think in the health space, certainly the data fusion products for PM 2.5 supporting health risk assessment is a very big one that is worth noting again. I think that also when we're tracking different emission sources, whether it's understanding what's really coming out of perhaps an unmonitored coal-fired power plant, or understanding where wildfires are occurring, or characterizing how different cities are increasing or decreasing their pollution. I think having this data set from space that is equal around the world or over a wide region is a big part of that. During the COVID-19 shutdowns in early 2020, a lot of sometimes even on the news, they showed some of these satellite products for air pollution, showing, for example, what a city's pollution was before the shutdown and after the shutdown. So you could look in the sky and see that it was maybe blue as opposed to gray, but to see it from space also allows us to put a number on it. Did it go down by a factor of 5? Did it go down by a factor of 2? In the United States, every year the EPA comes out with a report called Our Nation's Air, and that is primarily reporting what is coming from those ground-based monitors that we mentioned earlier in the episode. But for the past few years, they have also included satellite data, because then you can really see that the numbers just go down, 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 down over time. And it's a very powerful way to visualize and to see that what's happening isn't just in the cities where we have the monitors, but it's everywhere or almost everywhere across the US. So that's been one way it's been used. And maybe I'll tell one more story because this is one of my favorites, in part because it's so policy applied. That when we're thinking about health-based air pollution, of course, ozone is a really big issue. And ozone is a reactive gas that's associated with asthma and sometimes itchy eyes and premature mortality, a lot of negative health outcomes. Now, there are actually a lot of satellites that see ozone, but they mainly see ozone up in the stratosphere, the ozone layer. And because they're up in space looking down, and then we have this thick ozone layer over the Earth, it's actually very difficult to detect surface ozone from space. But ozone at the surface is cooked up from two ingredients, nitrogen oxides and volatile organic compounds, mostly. And satellites can see NO2, which is the main part of nitrogen oxides. And satellites can also see formaldehyde, which is a very reactive form of VOCs. And so when we're thinking about how do we actually control the ozone, what we really want to know is, should we turn down the NOx or should we turn down the VOCs, or do we need to turn down both? And this is really where satellite data can help us see which of these two is the limiting factor and inform policy actions, because if you don't know which is the problem, then it's hard to make good policies and invest in controls effectively.
No, that's so That's a really good example. And just for folks listening in, we want the ozone in the stratosphere because it protects us from UV radiation, but we don't want it around us. So I think that is a good application. That also reminds me of all the work that the HACAS team has been doing around the issue of ozone. And you talked a little bit about the project early on. I think what has been fascinating from my experience with the project is that it really tries to address the real world questions that people have, whether it is related to health or related to regulation or related to tracking how things are changing over time. And it's just such a multidisciplinary team, which is something that we want and need more of. So I'm curious if you can tell us a little bit, having led this work for such a long time, are there any surprising things that you have learned along the way in leading this work and sort of championing the use of satellite data for air quality and other related applications?
Well, I don't know if it's exactly surprising, but I'll just make the point that really the key has been to listen, because there are so many organizations that are working in air quality, that are working in health, that have really compelling needs for why they need more information. And it may be to design an intervention, or it may be for public outreach, or it may be to track volcanic emissions or whatever. But if we listen to what the information needs are, then that to me is such a powerful way to begin problem solving. And I guess maybe as a comparison, the traditional way that scientists do research is to come up with the problem in your own head, and then to come up with the way you're going to solve it, and then to go ahead. And, that obviously works for many, many things, and it's made a lot of great progress around air quality. But I think that this idea that there's a lot of questions out in the world, that if you listen, those can really spark scientific innovation. And so, I think to me, it's never gotten boring, and it's only gotten more and more exciting as we grow, engage more organizations, invite more people into this community and listen to what their needs are. Because as satellites are getting more advanced, we can tackle questions that we never could have tackled before. And there are more and more users out there who are hungry for the kind of data that these new technologies can provide.
Yeah. And I think, as someone who's engaged with the work a little bit, I will say, if you're listening to this and you're based in the US and you have questions that you think satellite data can help you answer, check out the project and try and attend a meeting. They tend to have so, in fact, there's one coming up in a month or so,
Yeah,
I guess.
exactly a month. Actually, it's November 6th and 7th in St. Louis at Washington University. Anyone can find more on our website at haqast.org. All of our meetings are recorded, so even if you're not in the U.S., you can watch the recordings and the live stream of our meeting. And we also have a lot of resources there for people who are interested in getting started using this data. So I hope that you'll visit our website and tune in. We love to connect with new audiences.
Amazing. So before we come to a close, I'm going to pivot a little bit to a slightly different part of what you've done for a long time, which is support other women in science. You were one of the
Mm-mm. Hi,
Hi,
Paula.
Tracy. Can you hear me?
Yes, yes. Not sure what happened.
Yeah, it looks like we're having trouble with our live streams these past two episodes. We've
Oh,
had something or the other. So sorry for that. I think what fun final question I was going to ask you was you've done so much work to both promote science as a field for all people and for the communities to connect with science with things like science-a-thon, but also you've done a lot of work to rally women in science, including being a member of the Earth Science Women's Network. And I just wanted to know, like, the motivation behind it and why and how that has been a part of what you do. And thank you for doing all of this.
well, thanks you for saying that, Pallavi. When I was a graduate student, I had a really great mentor and great colleagues, and I was having a lot of support in my life. But then I actually would go to some scientific meetings and connect with other young women in science. And we all were doing well, but we had issues that we felt like maybe were too personal to talk to our advisor about or too worky to talk to our best friends about. And we realized that there were a lot of issues that were affecting our path through our careers that was helpful to have peers and sort of people in the same boat to help you through. And over time, I think I've just realized more and more what are the things that are unique to the individual and what are sometimes the systematic barriers. For example, having childcare at a meeting can make the difference between parents being able to come, and that could be men or women. But sometimes those little barriers tend to add up more for women. So, I think that it really did not start in any political way. It was a very practical and I would say, self-centered need to have a support network. But once we realized that a support network was helpful to us in our own careers, then we wanted to grow it and make it more relevant to the next generation. So I think one of the things I'm most proud of in my career is starting the Earth Science Women's Network with a group of peers. And they have the tagline of supporting the scientist of today and welcoming the scientist of tomorrow. And I think that that's a really great way to think about it, because it's hard to build an on-ramp for the next generation if the current generation doesn't also get the support they need as they move through their careers. So thanks for being part of that.
No, thank you. Thank you for doing it. I think it's, incredibly important. And I have to tell you that it's the network and a lot of the work that you've done has been inspiration for me to start similar, very voluntary networks in South Asia and Africa. So we're still learning a lot from what you and your colleagues started. I guess we're coming to a close now. I feel like I could go on with this conversation and ask you more questions. It's clear that satellite data is really an exciting opportunity for us to learn so much more related to air pollution and also use it for health application and policy applications. So we look forward to seeing more of your work on this topic in years to come. And thank you very much for all the work you do as part of HeyCast and everything else. And all the best also for what comes next. And thank you for joining us today.
Thank you,
Um,
Paula. It's been a real pleasure.
Yeah, thanks a lot. And this month we are actually releasing our next edition of State of Global Air, which also, gets a lot of its information and data from satellite retrieval. So we're really excited to be launching it. And the next live stream in November is going to focus on findings from this new report. And we'll also hear from people that may be living with the kinds of diseases that are linked to air pollution. So join us then. And until then, check out our previous episodes. Sorry again for our technical difficulties. Second time in a row, we'll have to figure out what's going on. But thank you, everyone, and we'll see you next time. Thank you, Tracy. Bye.
Bye-bye.